Okay, so once more, hello everybody. So I would like to start with the words that today we learned about by very impressive talks all about electromagnetism. It's very young and active field, and now I am happy to present a talk about also one modern field of magnetism, which is curvilinear magnetism. So the curvilinear magnetism, it deals with conventional magnetic materials, and it's consider geometry governed effects. So by the influence of geometry, we mean the influence of local geometry like curvature, torsion, and the global geometry influence like topologies. And my special focus today will be about novel physical effects caused by tethering geometry, namely chiral symmetry breaking in a curvilinear magnetism. So I start to speak about curvilinear magnetism, and I spent a minute to introduce a subject. So curvilinear magnetism, it considers conventional nanowires and nanoshells, nanofilms with tethering geometry, and consider these effects caused by these geometry effects. The term curvilinear magnetism dated back to 2016 with the first review, so you see it's really young enough subject. And during this less than 10 years, curvilinear magnetism has an impressive progress. There appear a lot of systems and a lot of effects and a lot of applications, so they are reviewed in these articles, and probably everything which was done up to 2022 appeared in this book. So this year, the roadmap of three-dimensional nanomagnetism, it contains a review of current stage of curvilinear magnetism. So first of all, I'll start with the origin of curvature effects. It's connected with a special inversion symmetry. So if we start with a flat magnet, typically there is a special inversion symmetry in this system. For example, top and bottom surfaces of flat film are geometrically identical. But if we curved the film, we break this special inversion symmetry, and they appear due to local geometrical properties, so local curvature, torsion, so bending, twisting, they appear as geometry governed interactions, so effective interactions. So geometry governed anisotropy and geometry governed chiral interactions. So they result in geometrical magnetic chiral effects, which we will discuss today. The situation becomes more intriguing if we change the global geometrical properties, namely topology. They appear in new textures, and this is considered lead to phenomena like topological patterning. So to consider the impact of curvature on nanomagnets, we consider the typical model of a ferromagnet with four interactions like exchange, anisotropy, Dzerzhinsky-Moriya interaction, and magnetostatics. In principle, we can minimize the model considering just two interactions like exchange and anisotropy to understand most of ideas. And what is important that this is minimal model. It's lead to the standard Ginzburg-Landau function of the vector or the parameters. So it means that it's a very general model. So it can describe not only different magnets, but also liquid crystals, superconductors, and more. But how does the curvature get into the game? So it appears due to the geometry-dependent anisotropy. So the anisotropy direction, it fills the geometry. For example, if we speak about curved wire, so typically the anisotropy follow the wire, so it's tangential, it has tangential direction. So we consider the curved film the anisotropy is typically determined by the normal direction to the surface. And what is important, if the anisotropy is strong enough, it dictates the receivable magnetization distribution, and it gives a hint that all the interactions should be considered in the curvilinear reference frame. And this leads to a restructuring of all energy terms which contain the special derivatives of magnetization. Here you see the typical this destruction of energy in of the magnets. So here in naught is the energy term which do not depend on this geometrical properties of the local curvature. The next term, effective anisotropy, it contains the effects of intrinsic magnetocrystalline anisotropy and geometrical extrinsic effect. They can come from exchange interaction. In this case, they are typically quadratic in curvature, and they can come from Dzerzhinsky-Morier interaction. Here, the effective intensity is linear in curvature. But finally, we have the biaxial anisotropy and geometrical effects are determined by two principal curvatures. So in the case of film, or curvature torsion in case of wire. The next contribution is a mesoscale Dzerzhinsky-Morier interaction. So it again contains the intrinsic, so material dependent Dzerzhinsky-Morier interaction, and geometrical contribution which come from exchange. And the coefficient of exchange contribution, they are typically linear with respect to curvature. But what is important is the symmetry, which is dictated by this Lifshitz invariance. It takes the same form as the well-known interfacial Dzerzhinsky-Morier interaction for example, in fields which is known to lead to helical structures, skirmion crystals, and more. And what is the consequence of this effective interaction? So effective anisotropy leads to topological patterning, and this mesoscale Dzerzhinsky interaction lead to geometrical magnetochiral effects, which we will discuss today. I start with local chiral effects, which are induced by curvature. What is important that these local chiral effects, they appear also in a non-chiral structures. For example, they can appear in a flat parabolic nanostripes, and they dictate that the domain walls have some preferable direction, so a preferable handedness. So, for example, you see here that head-to-head domain walls is always directed outward, and tail-to-tail domain wall is always directed inward. They are pinned in the maximum of curvature. We can be excited, and there are a lot of interesting studies. And what is important that it's not also theoretical predictions, but it was the Dzerzhinsky-Morier interaction was quantified experimentally by measuring the dependent field in this system. So in systems where there is a geometrical chirality, for example, in a helix, so there exist left or right helices, and they appear a coupling between geometrical chirality and magnetochirality, which lead to, for example, preferable direction of domain walls in this system. In a helicoid ribbon, they appear the preferable handedness of the ground state. In a more complex structures, like, for example, in toroidal shells, they appear as specific vortices outward and anti-vortices in inward. In another shells, for example, the local curvature dictates and chooses the different type of excitations, Meron-like excitation. For example, in a parabolic shell, they appear a vortex, and hyperboloid shell, it hosts anti-vortex. And for example, in a spherical shell, it can host skyrmion as a without intrinsic Delafinsky-Marie interaction. So next, I would like to results how what appear dynamically. So the interesting effect and the consequence of this local chirality is the geometry induced automotion of domain walls that were predicted for the Euler spiral, and it was experiments were realized for a flat Archimedal spiral and three-dimensional nanoconduit. What is important that in experimental studies, the technique of nanoprinting produce the thickness gradient, and it was expected to be the main factor of the force which causes the domain wall motion. So our theoretical predictions, they results in the domain wall moves by the gradient of the curvature, but experiment suggested that they could appear another effect. That is why we decided to study the effects of another geometrical effects of the varying thickness, and we realized that we started with the flat systems and realized that domain walls can be pinned by the varying thickness, and we can excite excitations of the by magnetic field. We can excite the oscillators of the domain wall, and the frequencies of this domain wall are determined by both curvature gradient and the thickness gradient. And later we study the domain wall motion due to the varying cross section, and they appear a lot of interesting results here. They will be presented today in the talk by Dr. Karakuts. Next, I would like to explain one more effect, local chiral effects, a coupling between geometrical chirality of the substrate, the magnetic chirality of the texture, and neutrino topology. Right here, you see you see the Möbius ring. Geometrically, there exist two rings, right hand, the left hand Möbius. Depending on the geometrical and magnetic parameters, there can appear a lot of different structures, a lot of, for example, water structure, different domain walls here, and probably most interesting case, if appear in when we magnetize the Möbius perpendicularly, due to the topology, they appear discontinuity, which results in the appearance of the so-called topologically protected domain wall. And this domain wall is characterized by chirality, so now magnetization is changed here from the outward to inward, or it could be opposite. And the theory predicts that there is a coupling between this geometrical and magnetic chirality. So one word like here is energetically preferable. It has minimum energy. It was realized in macromagnetic simulations. And later, these magnetic Möbius rings were fabricated experimentally using fabric technique. Next, I would like to mention one more very interesting effect caused local chiral effects caused by exchange-driven Delafinsky-Marie interaction for the skyrmion texture. So there are two mechanisms of the geometry influence on the skyrmion. One is the formation of the small radius skyrmions just by the mean curvature. So the skyrmion is localized you see small radius string localized in the maximum of the curvature. Another idea is the appearance of tunable and in particular large radius skirmons. The radius is determined by the gradient of the curvature. And these theoretical ideas they correlate with the experimental results. So you see experiments with two different geometries. So it was periodic, self-assembled periodic system of nanocones or spherical nano-indentations, and after that it was deposed a perpendicular material, and they appear a structure which correlates with theoretical results. And so skirmion-like structures. One more effect is the mesoscale Dzerzhinsky-Morier interaction. The main idea is we have two Dzerzhinsky-Morier interactions. Intrinsic Dzerzhinsky-Morier interaction caused by material parameters and extrinsic caused by geometry. What is important that they have different scales, they can have different directions and different symmetries. So tuning geometrical parameters, we can change as magnitude as the direction of the Dzerzhinsky vector and corresponding effects and symmetry of Dzerzhinsky-Morier interaction. So how we can use it? So first idea was the concept of artificial magnetoelectric materials when by the geometrical theory we can change essentially the states of these magnetic materials. And another is the appearance of the configurable skirmal lattice. So if we have geometrically lattice with this hills, it can support different types of skirmons, described before, small and large radius skirmons, and moreover, these skirmons can form a ground state of this lattice, and by applying field, we can switch one skirmon to another one, and it's an idea to use it as to decode information, so like 0 and 1. So most of the effects which I described up to now were about local chiral effects. They were connected with the Heisenberg exchange, with the anisotropy and Dzerzhinsky-Morier interactions. Moreover, if we consider a flat system, there are no non-local chiral interaction at all. And now I will try to explain how non-local chiral interactions can appear in curved magnetic systems. So to get an idea how to treat non-local magnetostatics in a curved system, the new idea was to use 3 fixtures magnetostatic charges. So the typical picture is you can see the volume and surface charges, but here in the curved system, the idea is to use tangential charge, geometrical charge, and surface charge. So tangential charge is determined by the tangential derivatives, so determined by the tangential components of magnetization only, and it corresponds to the volume charge in the flat system. And the new guy is the geometrical charge. So you see it's determined by the curvilinear geometry, so in the mean curvature. And it also depends on the magnetic texture. So it's coupled the curvilinear geometry and magnetic texture. And now we can go back to the energy contribution. So we already considered the effective anisotropy and mesoscale, DMI, so it's local energy terms. And now we discuss the magnetostatic interaction. So you see that all these magnetic charges, so tangential, geometrical, and surface, they interact pairwise. So here there is no interaction in a flat system. In a curved system, they are interact, all these charges. And they all produce contributions. So there is only one local contribution between surface charges. It contributes to anisotropy. We all know it's particularly the shape anisotropy. But all other contributions from the magnetostatics are essentially non-local, and they form non-local shape contribution and non-local curvature induced contribution to the effective energy. Now we can analyze all this contribution and make a conclusion about possible effects. Now I would like to tell some words about these effective interactions which appear in magnetic system and okay. So from the symmetrical point of view, so if effective interaction does not break the special symmetry, it can lead to effective anisotropy. So it's local interaction, so driven by discuss exchange, Diokshinsky-Marie interaction, shape anisotropy, or it can be non-local, driven by magnetostatics. And it finally, these effective interactions lead to a kind of effect which we call topological pattern. But if this effective interactions break the special symmetry, it produce these chiral effects. So again, they can be local, driven, for example, by exchange, like resulting in this mesoscale Diokshinsky-Marie interaction, or it can be non-local, driven by magnetostatics. All they produce geometrical magnetic chiral effects. Now we'll speak about these different interactions. So we construct the framework of curvilinear magnetism with account of all these interactions. So and analyze the interplay between symmetry of different all these interactions, the geometry of the system, and different textures, and make conclusions about influence of these interactions. And finally, we found that they appear this combination when the non-local magnetostatics can work and can in what geometries it can produce some interesting non-local effects. And now I would like to mention some of these effects. So first I start with so-called pattern-induced chirality breaking. It means that we consider the situation when the symmetry of the system is so high that the static magnetization texture is degenerated with respect to chirality. And the effects of chirality breaking appear geometrically. For example, if we consider two magnetic nanotubes with a vortex domain walls with opposite chiralities, counterclockwise or clockwise, so they have the same energy. But if we apply the magnetic field, the domain walls start to move, and the motion is dependent on the chirality. You see that typical dependence velocity of the wall of the field depends on the chirality, and they appear so-called chiral breakdown, so the break of the chirality of the domain wall. Another consequence is the suppression of the Walker breakdown, and it's connected to the spin-Cherenkov effect for the magnons. So all they are connected to the pattern-induced chirality breaking, and all of these effects they are described by the interaction between the geometrical and tangential charge, or surface and tangential charges. And also, I hear one more effect is the nanotube, is the reciprocal motion of the spin waves. if we're speaking about chiralities breaking, I would like to mention one more very interesting effect. So if we consider biaxial nanotubes with mesoscale DMI, so it means that it has the intrinsic geosynchronous interaction as a geometrical effect, the interplay of this effect. In fact, local and non-local, they appear chiral symmetry breakdown. It will be done in the next talk by Svetlana Kundovich. Recently, we have studied non-local chiral effects both theoretically and experimentally in a system with asymmetric nanovortex cap. So the effect leads to the coupling between the magnetic chirality of the texture and the geometrical chirality of the vortex string. So to explain an idea, I start with a flat system, flat the vortex in a flat disk. So the topological properties of the vortex are characterized by the vortex polarity, which is direction of the magnetization in the vortex core, up or down. And you see this direction of the vortex magnetization in the core is formed here a vertical vortex string. Another topological characteristic is a chirality, it's direction of magnetization along the edge, counterclockwise or clockwise. And the product of this circulation and polarity, it produces the magnetic chirality of the vortex, which is plus minus 1. Okay, so experimentally, it was studied the asymmetric nanocaps. So, and when the upper surface is asymmetric and the vortex it's shifted from the peak, and they appear a vortex string, which is not a line, but the analysis, so experiments and micromagnetic simulations show that it has a form of a helix. So as we know, there exist left or right-handed helices, and what was found that there appear a coupling between the geometrical chirality of the helix and the magnetic chirality of the vortex. So, and calculations, theory also confirm this result. And what is important that here one of the important contribution is the dependent so interaction between the surface and volume charges, which is not typical with a flat system. So, and last picture here is that very recently this interaction between a volume and surface charges was analyzed in this this curved nanoflowers that lead to the shift of the vortex from its center. So to end my talk, to sum up results, I would like to say that curvilinear magnetism is a branch of the material science which give a possibility to just by bending or twisting conventional magnetic fields obtain the magneto-chiral and anisotropic response. And curvilinear magnetism, it's already found a lot of applications. So now it's very impressive progress in the shapeable magnetic electronics, curvilinear spintronics, curvilinear skyrmionics, curvilinear magnonics. And this year they appear first results, first papers about curvilinear effects in the outer methods. So at the end, I would like to thank several groups. First of all, our written team, which is a joint team between Taras Shevchenko, the National University of Kyiv, and Bogolyubov Institute for Theoretical Physics. Here I mentioned people who are originated from this group now working in different communities. And also I would like to thank collaborators, a group of Denis Makarov, Ivan Van Brink, Alex Saxena, Pedro Landinas, and Valery Slastik. So, thank you for your attention.
So unfortunately, our timer is over. I grant to one very quick question. Simple. Super quick.
Yes.
Dmitry, thank you very much for the profound speech with many informative pictures. And my question will be really simple. At the beginning of your speech, you mentioned that there is a strict border between outer magnets and curvilinear magnetism. So would you envision their connection in future?
Okay. Yeah, unfortunately, I never work in outer magnet, but I can say that okay, this year they appear a great paper by Yaron and Kolosis with
and more.
yeah, with about coverage effects in the outer magnet. So I think that the main ideas which I mentioned are so general. So I also thought that they can apply magnetism in fact, in all the system, when the all collinear system, when you have a partial derivatives and you have a vector of the parameters.
Right. Yeah. Thank you very much.
Yeah.
Well, let's thank our speaker again.